NASA has 30 years of data on how humans survive deep space, on what slowly breaks astronauts down, not oxygen deprivation, not radiation, but the environment they live in. SpaceX knows that, and they're still designing Starship differently, not because they haven't read the data, but because they're betting on something NASA doesn't have. And if that bet is wrong, we won't find out until we're already 9 months into a Mars transit. Today we break down both sides. Let's start with a simple question. Why do people die in space? The obvious answers: radiation, oxygen loss, pressure failure, physical threats, measurable threats. But NASA has a different list. It's called the 5 hazards of deep space human spaceflight. And 3 of those 5 have nothing to do with the rocket, nothing to do with the engines, nothing to do with propellant. They have everything to do with the crew, specifically isolation and confinement, distance from Earth, closed and hostile environments. Those 3 sound like psychology problems, something for doctors, not engineers. That's the wrong frame. Think about isolation this way. You're flying to Mars, 9 months in transit, and one crew member starts fading. Not sick, not injured, just shutting down, sleeping more, talking less, working slower. Mars 500 was the longest Mars transit simulation in history. 6 people, 520 days inside a sealed steel module in Moscow. According to a study published in The Lancet in 2014, after month 4, crew activity levels dropped an average of 25%. Sleep disruption increased and never stopped. But here's the detail most summaries skip. One specific crew member entered what researchers called psychological hibernation, nearly non-functional for weeks at a time. Not because he was weak, he was carefully selected, rigorously trained. The environment simply won. Now place that person at the controls of the ship's life support system, with a 22-minute one-way communication delay to Earth, and mission control unable to intervene in real time. This is no longer a psychology problem. This is an engineering problem. And isolation is just one of the 3. Distance from Earth creates a separate issue. Call it autonomous cognitive performance. On every shuttle flight, every Apollo mission, every Dragon crew rotation, astronauts knew Earth was watching every second. Mission control could intervene almost instantly. That awareness carries real psychological value. On a Mars transit, it disappears. The communication delay runs 3 to 22 minutes one way, depending on the relative positions of the 2 planets. That means when the crew reports an emergency, the earliest they hear back is 6 minutes. The latest is 44 minutes. In an actual emergency, 44 minutes is an eternity. The crew must assess, decide, act, potentially after 6 months of isolation, with degraded judgment and no real-time backup. Cognitive performance under stress, after months of confinement, that's an engineering parameter, not a soft metric. You design the habitat to maximize that performance, or you don't, and the outcomes are completely different. The 3rd hazard is the closed environment itself, and this is where the hardest data lives, and data most people haven't heard. On the ISS, CO2 partial pressure is maintained at roughly 0.5%. That sounds abstract. Here's the context. Earth's atmospheric CO2 sits around 0.04%. ISS runs more than 10 times higher. And in NASA-published studies, prolonged exposure at those CO2 levels shows documented correlation with headaches, fatigue, and most critically, degraded cognitive performance on complex decision-making tasks. That's a pipe sizing problem, an airflow design problem, a ventilation engineering problem, not psychology. Fluid dynamics. So what do all 3 hazards have in common? They share exactly one real solution: the physical design of the living environment. You cannot train a crew member to be immune to 9 months of confinement. You cannot write a procedure to override CO2-induced cognitive decline. You cannot motivate someone out of psychological hibernation with a team meeting. You have to design the habitat right from the start. That's why NASA has spent 30 years studying exactly this. Not because they enjoy research, because this is an engineering requirement for any crewed deep space mission. NASA's 30 years, strong data, no hardware. NASA didn't launch behavioral health research because of an accident. They launched it because they looked at the trajectory of the space program and recognized if we want to send people farther than the ISS, farther out, longer duration, we need to understand what happens to them before we go. That's sound engineering thinking. Research first, hardware second, and the research infrastructure they built is genuinely impressive. HISEAS, the Hawaii Space Exploration Analog and Simulation, was a NASA-funded program running from 2013 to 2017. 6 missions. Crews living inside a small habitat on the slopes of Mauna Loa, designed to simulate Mars surface conditions. But here's the detail most summaries leave out. Across several missions, researchers tested what they called biophilic elements, artificial plants, nature soundscapes, lighting designed to mimic natural day-night cycles. Result: crews in habitats with biophilic elements reported stress levels 20% lower than control groups under identical isolation conditions. 20% from artificial plants and recorded birdsong. So when someone proposes putting greenery inside Starship, that's not an aesthetic choice. That's implementation of a tested, published engineering finding. HISEAS is just one piece. NASA also ran Scott Kelly's year-long ISS mission, the longest twin study in history. Scott Kelly spent 340 days on the ISS. His twin brother Mark stayed on Earth. Same DNA, different environments. NASA's published results. Scott Kelly's cognitive performance in specific domains, particularly processing speed and accuracy under time pressure, tested lower than Mark Kelly's after the mission. 340 days on the ISS, with all the support of a modern space station, with near real-time communication to Earth. A Mars transit is 270 days one way. No space station, no real-time comms. All of that data was consolidated into one document, the NASA Human Integration Design Handbook, nearly 1,000 pages. This is not a suggestion document, it's engineering requirements for habitat. Design. Minimum volume per person. Lighting spectrum specifications. Not standard white light, but specific spectra that regulate circadian rhythm and sleep quality. Noise thresholds. Because chronic subpain threshold noise exposure still carries documented cognitive effects. Private space requirements, because crew members need the ability to physically separate from each other, not just mentally. 30 years of research, distilled into specs. So which hardware has NASA actually deployed those specs into? Honest answer, almost none. The ISS was designed before most of this research was completed. It's a product of the 1980s and 1990s, before HISEAS, before Mars 500, before the Twin Study. And Orion, NASA's only flying deep space capsule, has roughly 9 cubic meters of pressurized volume for 4 crew members. Here's what that number actually means. The Apollo Command Module, the vehicle that flew humans to the moon in 1969, had approximately 6 cubic meters for 3 crew, roughly 2 cubic meters per person. Orion has 9 cubic meters for 4 crew. That's approximately 2.25 cubic meters per person. 50 years later, we gained 0.25 cubic meters per person. This isn't because NASA didn't know they needed more. It's because the SLS mass budget wouldn't allow it. Orion was constrained by an architectural decision made before the habitability research was completed. And once a design is locked in, you can't add volume. You optimize within the constraint and that's all you can do. NASA has the data, NASA has the requirements, but NASA doesn't have a vehicle large enough to implement them. That's the structural bottleneck. Not a knowledge gap, a vehicle gap. If you follow this channel for this kind of deep dive analysis, subscribe and turn on notifications. It genuinely helps this content reach more people. Now let's get into the part I find most interesting. SpaceX's approach, volume is the play. SpaceX did not approach habitability the way NASA approached it. No analog mission program, no 30-year research track, no 1,000-page habitat design requirements document before hardware development began. The instinctive reaction is, so they're doing it wrong. But hold on, look at one number. Starship has approximately 1,000 cubic meters of pressurized volume. That number needs a reference point to land. The ISS, built over more than a decade, with contributions from 15 nations at a total cost exceeding $150 billion, has roughly 916 cubic meters of pressurized volume. For 6 resident crew members, Starship has more than the ISS. In a single vehicle, assume a Starship Mars mission carries 6 people. Volume per person comes out to roughly 166 cubic meters. Compare that to Orion at 2.25 cubic meters per person. Compare that to Apollo at 2 cubic meters per person. This is not a 2 times or 3 times difference. This is a 70 times difference. But raw volume is not habitability. This is where a lot of people get it wrong. You can have 1,000 cubic meters and still design an environment that produces every problem NASA has documented, if you don't use that volume correctly. What volume does provide is architectural flexibility that Orion simply doesn't have. Specifically, private quarters. The NASA Human Integration Design Handbook identifies private space as a requirement, not a luxury. On Orion, there's no room for it. On Starship, there is. Adequate exercise infrastructure, bone and muscle loss in microgravity begins within the first week. ISS astronauts exercise 2 hours per day as a medical requirement. On Orion, with 2.25 cubic meters per person, that's impossible. On Starship, it's possible. Biophilic design, artificial plants, natural spectrum lighting, ambient soundscapes. The elements high seas demonstrated have measurable effects on stress levels, impossible to implement on Orion, implementable on Starship. So what is SpaceX actually doing with that volume? Honestly, we don't fully know yet. SpaceX doesn't have a track record of publishing interior design philosophy the way NASA publishes research. What we know comes from renders, hints in official statements, and, as you've seen, the occasional tweet. But here's the angle I want you to consider. SpaceX is famous for build first, collect data after. You've seen it with Raptor, rapid iterations, continuous design changes, driven by real test data. You've seen it with pad design. Flight 1 destroyed the pad, Flight 12 left it nearly intact. But with habitability, they're doing something different. They're not rapidly iterating on a small habitat. They're building a habitat large enough that every future iteration can happen inside it. That's a fundamentally different architectural bet. NASA's bet: research first, then hardware. SpaceX's bet: large enough hardware first, then fill in the details. Both have engineering logic. Both carry different risk profiles. What's the risk of NASA's approach? Strong research, high-quality data, but no hardware to implement it. 30 years of knowledge sitting in documents, with no vehicle capable of deploying it. What's the risk of SpaceX's approach? Hardware large enough to implement nearly every habitability requirement, but behavioral data for 9-month transit conditions doesn't exist yet. No one has ever lived 9 months inside a Starship-class habitat under simulated Mars transit conditions. If SpaceX's bet pays off, the volume allows them to implement and iterate on habitability solutions during actual operations. The first Mars crew becomes the first test subjects in an entirely new habitat class. If SpaceX's bet is wrong, they won't know it until the crew is 3 months into the transit, past the point of no return. The commercial approach, when habitability becomes a selling point. There's a third player in this story, and they're doing something neither NASA nor SpaceX has done. Orbital Reef, the commercial space station being developed by Blue Origin and Sierra Space, was designed with habitability as a primary requirement from day one. Not an afterthought, not a constraint to accommodate, a selling point. The reason is simple. Orbital Reef's customers are commercial. Researchers, tourists, private astronauts paying real money, and people paying real money to live in space will demand a better experience, or at minimum, one that isn't miserable. Commercial pressure does what government mandates cannot. It creates a financial incentive to make habitability better. Axiom Space takes it one step further. Axiom's modules, currently being attached to the ISS, eventually separating into an independent station, have interiors designed by Philippe Starck, a professional industrial designer. For the first time in spaceflight history, someone professionally trained in human-centered design was involved from the concept stage, before engineering constraints were locked in. Why does that matter? Look at aviation history. Early aircraft cabins were designed by engineers. Seats, windows, aisles, all optimized for structural efficiency. Passenger experience was whatever was left over after engineering was done. Gradually, airlines realized passenger experience directly affected revenue. Industrial designers were brought in. Ergonomics were studied. Lighting was researched. Cabin design improved, not because regulation required it, but because the market demanded it. Commercial space is following the same trajectory, moving significantly faster than government programs. But here's what all three approaches are missing. NASA has data from Mars 500 and HICs, but both carry one critical limitation. Mars 500 used a small habitat, nowhere near Starship class volume. HICs used a habitat of roughly 111 square meters. The longest mission ran 8 months. Nobody has data on a 9-month transit in Starship class volume. Not because they didn't want it, because that hardware hasn't existed long enough to generate it. Orbital Reef and Axiom will generate habitability data in the coming years, but that's LEO data, low Earth orbit. Crew still has real-time communication with Earth. Emergency return is still possible within hours. The psychological environment of a LEO is fundamentally different from a Mars transit. The real gap in this industry isn't a lack of research. The gap is the absence of long-duration transit data in large volume habitats, under conditions with no rescue option. And that data can only be generated one way, by actually flying. 3 risk profiles and the question the industry hasn't answered. Let's pull it all together. 3 approaches, 3 distinct risk profiles. NASA, strong research methodology, high-quality data, but no hardware to implement it. The risk is that knowledge never reaches application before the missions happen. SpaceX, hardware large enough to implement nearly every requirement, but behavioral data for transit conditions doesn't exist yet. The risk is discovering unknown unknowns mid-mission. Commercial stations, habitability prioritized from the start. Commercial incentives drive innovation. But the data being generated is LEO data, not Mars transit relevant data. All 3 are running in parallel. And in this decade, as Axiom and Orbital Reef come online, as Starship advances toward crewed operations, there is a window. Data from commercial stations could inform Starship interior design before the first crewed Mars transit happens, but only if the research is designed correctly. Here's the real question the industry needs to answer. Not which engine is better, not who gets to Mars first. The question is, will behavioral health data collected from commercial LEO stations between 2026 and 2030 be specifically designed to capture Mars transit relevant variables? Because if Axiom and Orbital Reef are collecting data on tourist comfort, aesthetics, short-term well-being, overall satisfaction, that data is useful, but it's not sufficient for a mission with no abort option. Mars transit relevant data needs to capture different things entirely. Cognitive performance, after months 4, 5, and 6. Crew dynamics with simulated communication delay. Decision-making quality under simulated emergency conditions after extended isolation. The measurable effects of biophilic elements on performance, not just self-reported stress. That's a completely different research agenda from how do we make the tourist experience comfortable. NASA knows this. The Human Research Program has published highly specific requirements for analog missions. But NASA doesn't operate Axiom, doesn't operate Orbital Reef. And Blue Origin, the company building Orbital Reef, just lost a launch pad. Commercial station timelines are being compressed from multiple directions simultaneously. There's one more detail in this picture that almost no one is talking about. NASA's Human Research Program has an annual budget of approximately $20 million for behavioral health research. $20 million. For one of the 5 hazards NASA itself identified as top priorities for deep space human spaceflight. For context, NASA's Artemis program budget in 2024 was approximately $8 billion. That ratio is 1 to 400. You are investing $400 toward the rocket that gets people to Mars, and $1 toward understanding whether those people will still be cognitively functional when they arrive. This isn't a criticism of NASA specifically. It's a structural priority across the entire industry, an industry measured by launches, not by crew cognitive performance after 9 months in transit. And this is where the story loops back to SpaceX. SpaceX is building a vehicle with volume large enough to implement every habitability requirement NASA has ever researched. That's real. But volume is not automatically habitability. Volume is an enabling condition. What gets placed inside that volume, the design of the living space, the lighting, the private areas, the biophilic elements, the exercise infrastructure, that's what actually determines the outcome. And those decisions are being made right now, while Starship is still being iterated, while interior design is still being finalized. This is the window, and it won't stay open. When Starship is certified for crewed missions, when the interior is locked in, when hardware is built, changing fundamental architectural decisions about habitability becomes extremely difficult. The same way NASA couldn't add volume to Orion after the design was frozen. So is SpaceX actually using NASA's 30 years of data? Honest answer, we don't fully know. SpaceX doesn't publish interior design process details the way NASA publishes research. What we have are renders, hints, and signals from public statements. But here's what we can say with confidence. SpaceX is building hardware large enough that NASA's requirements could be implemented. That's step 1. Step 2, whether those requirements are actually being implemented or whether it's just volume without the right design intent. That's a question we'll have a clearer answer to as Starship moves closer to crewed operations. Mars 500 ended in November 2011. 6 people stepped out of a steel module after 520 days. That data was published, cited, archived in NASA's Human Research Program. And the first crew of an actual Mars transit, people who will live inside a habitat many times larger than Mars 500, farther out, longer duration with no rescue option, will be the first true test subjects under those conditions. Not because we lack data, but because the best possible data on a 9-month Mars transit in Starship-class volume can only come from the transit itself. The question isn't whether we'll have enough data before we fly. The question is, have we used everything we already have before that window closes? NASA has the data. SpaceX has the hardware. But data doesn't load itself into hardware. The people making those decisions are making them right now. What habitability variable do you think is most critical and most overlooked? Drop it in the comments. I read every one. Subscribe to the Space Brief if you want to keep going deep on questions like these. And tap the next video to keep watching.